For the people who don't know me, I'm Plamen Krastev from Research Computing. And before coming to Harvard, I was at the Lawrence Livermore National Lab. My background is in theoretical and computational nuclear physics and astrophysics. And at Lawrence Livermore, I developed a very large-scale shell model computer codes in the context of nuclear theory using some of the largest and fastest supercomputers on the planet. And basically, this is what got me interested in the world of HPC, or high-performance computing. And here at Harvard, I'm helping researchers with scaling up their workflows and also doing a lot of optimization and debugging of various workflows, in particular parallel workflows using technologies like OpenACC, MPI, and GPU computing. I also do a lot of scientific software support and pretty much everything else that comes in between. And also I'm involved with the training, writing a lot of documentation and everything else that comes in between. So today I'm going to be talking about GPU computing on the FAS Research Computing cluster canon. And basically the idea is to help you to understand how to run your applications as effectively as possible, in particular the GPU applications of the cluster. So the next topic that I'm going to discuss here are our objectives. Like I mentioned, the first objective is really to advise you on the best practices for running your GPU applications on the cluster. And while I'm not going to teach you really how to do a full-fledged parallelization using GPUs, basically with some examples, I'm going to provide really the basic knowledge which is required to build your own GPU applications if you're interested in this. So let's just say a few words about the FAS Research Computing group, from which I'm a part of. Maybe most of you already know about our group. So basically, the major idea of our group is to help researchers to do their research work by providing computational resources. And the primary resource that we provide is the Canon supercomputing environment, or we call it environment because it is really a heterogeneous cluster, which what is relevant to our presentation also includes some GPU nodes which can be used for GPU computing. The research computing staff currently includes more than 25 people which have various backgrounds. Like I said, I have background in nuclear theory. We have also people with background in other domains like physics, astrophysics, life sciences, and also a lot of system administrators and software developers. We support more than 600 research groups and very large population of users across all departments of FAS and also CES, the Center for Astrophysics, and some other schools. And we also get help from the bioinformatics group, which is part also of FAS, which handles requests which are related to life sciences. So the major environment that we support here is the Canon cluster, and the Canon cluster has more than 100,000 compute cores. And what is relevant to this talk, we also have nodes which are GPU cards, and currently we have A100s and H100 GPU cards which provide really access to a bleeding-edge GPU computing. The software on the cluster, currently the operating system is Rocky 8. The job orchestration is done through the Slurm job scheduler, which is responsible for managing the jobs and the workflows which are submitted to the cluster, requesting specific resources and so on. And all these compute resources, they're interconnected with a very fast network, infinite band network, which provides a very fast operation and inter-node communication, and also communication with the storage which is attached to the cluster. So what is really GPU? Because we're going to talk about GPU computing. So GPU really stands for General Purpose Graphical Processing Unit, where basically here we go beyond simply the processing of graphical information, but these units are used for actual computation. So here, as pictured on this illustration, we compare CPU to a GPU. So while the CPU, a typical CPU, would have multiple cores, for example, on your laptop, nowadays it's very typical to have something like a CPU with 4 or even 8 cores. A GPU can have thousands of cores, which would provide a much greater level of parallelization, so it can do much larger computations and it can dramatically accelerate the computations. So that's actually the major reason for using GPUs. Here on this slide, we briefly will touch some of the similarities and differences between the GPUs and CPUs. So you all know that CPU stands for Central Processing Unit, the GPU is the Graphical Processing Unit. Like I said, the CPU has several cores, while the GPU will have many cores. The CPUs, on the other hand, are optimized for a very low latency, and they're very well optimized for serial processing. Basically, serial processing means that at every single time you can actually execute only one operation. While the GPU is good for parallel computing and they're optimized for a high throughput computing. And when we say parallel computing here, we mean that in a single moment of time, you can do multiple operations, which really allows for dramatic acceleration of the computational work. And here I have some links which can provide more information about the nature of the GPUs and why they're good for scientific and technical computing. So on this slide, I'm going to talk a little bit about heterogeneous computing, and basically the GPUs provide the ability to do serial and also parallel computing within the same environment. What this means that basically if you have, let's say, a typical application code, the most time-consuming number crunching parts of the code, the most compute-intensive parts, can be offloaded to a GPU to do the parallel processing. And then once this part of the code is completed, then the code can continue the rest of the operations in serial. So this is to what we refer as heterogeneous computing, like illustrated here in this site. So basically, the GPUs enable applications to run in parallel, but for this to happen, you need to have a parallel computing platform or environment. Like in case we have the Canon computing cluster, and in addition to that, you need to have application programming interface, which allows you to write a code which can take the full power of the GPUs. And the GPUs support several types of memory. So the GPU memory is used to transfer data between the device and the host shared memory in an efficient way for the threads in the same block to share their runtime and data, like is illustrated here in this site. So on this slide here, I'm just going to talk about some examples of GPU accelerated applications. So very large modern applications in technical computing and also in scientific computing already took advantage of the GPUs. So many of fault legacy codes has been rewritten in a way so that it can use the power of the GPUs. And here I'm just going to give you some examples. Really, the GPUs took off in the age of artificial intelligence, and all modern deep learning frameworks like TensorFlow, PyTorch, and JAX that we have on the cluster, and we have the ability to run this, have actually, they use GPUs for the acceleration and for training of the neural networks and so on. So these libraries can be very easily installed on the cluster via pip or conda mamba, and we have documentation which allows you to install and use these applications and libraries on the cluster for your research. In addition to that, applications like MATLAB also support GPU computing through PCT, where PCT here stands for the Parallel Computing Toolbox, which provides MATLAB with the ability to run in parallel, both on a single node and also in a multi-node computation. And also there, just to continue with the examples, there are many other applications which are specifically built CUDA, which is the NVIDIA implementation of a library which allows for doing parallel computations using GPUs. And another thing, maybe you're already aware of that, NVIDIA provides already many applications which are optimized for using NVIDIA GPUs on their NVIDIA Cloud Computing Platform through their catalog, which come as a containers. Although I'm not gonna specifically talk about containers, maybe this is one of the easiest way and fastest way to grab some application which is optimized for running on the NVIDIA GPUs and use it on the cluster. So the next topic that I'm going to discuss here are basically the ways to accelerate your applications using GPUs. And there are three different ways, just put in short, to accelerate your applications. One of these is to use libraries. Another one is to use the OpenACC, which stands for Open Accelerator, and I'm going to talk a little bit about this just in a second, a few more slides down the road. And OpenACC allows you to use directives, which are like comments in the code, but they have specific meaning to the code so that you can run your applications on GPUs. And another approach would be to use programming languages, which would allow for a maximum flexibility, but it's a little more involving. So the libraries would be the easiest way to parallelize your applications and make the full benefit of GPU. Basically, these libraries, they're optimized, many of these come from NVIDIA, to use GPUs, and these are numeric libraries, and others which, for example, are libraries that can do a lot of visualization and things like that, that can make use of GPUs. Like I said, I'm going to talk more about the OpenACC, but it is also a very easy and straightforward way to parallelize your applications for GPUs. The programming languages, they would allow for maximum flexibility, of course, but the learning curve could be a little steeper. Although they allow for maximum flexibility, the full responsibility actually falls on the programmer, because you should know exactly what you're doing when you use this specific approach. So here on this slide, I'm including some examples of the GPU accelerated libraries, and a very notorious example would be the NVIDIA CUDA BLAS, which is the GPU version of the BLAS library, which provides routines for doing common linear algebra operations like dot products of vectors or matrix vector multiplication or multiplication of matrices and things like that. And if you go to this link over here, which is provided on the slide, you will see a list of many other libraries which may be relevant to your computations. And I think this list continuously growing because more and more scientific libraries are optimized for GPU acceleration. So the next topic that I would like to discuss in here, we're going to dive into a little more details how to make use of these approaches that I just mentioned a few slides ago. Here we're going to talk how to use, in particular, optimized libraries like the CUDA BLAS. And for that specific illustration, we're going to use a specific example which will illustrate how to parallelize the single precision A multiplied by X plus Y operation, or the SAC pool. So that's here on this slide, the CPU version of the code, where I just wrote a very simple vanilla C code, which just illustrate this. I'm not gonna get into details, but I'm just gonna show you on this slide over here, the GPU version. And when I say GPU version, this illustrates the usage of the CUDA BLAS, which comes with a CUDA module that we have on the cluster. So it's very easy to do that. you just have to include several other headers and also call the specific routine from the CUDA BLAST library, which actually handles the operation that we're talking about over here. And the full example is available at this link over here. Like I said, I'm not going to really teach you how to do GPU, how to program you for the GPUs, but the major focus of the talk is really to illustrate how to use the GPU resources that we have in the cluster and how to run your applications that you may have from somewhere else or develop something in your lab. So the first thing that we have to do is actually, for that specific example, is to compile it. And the CPU version, because this is a C code, would require the GNU compiler or the GCC. I assume that you're already familiar with our system and with the way how the software works on the cluster. So to get a specific version of compiler, in that case GCC, you load the software module. The command for doing this, module load, followed by the specific module name, which in this case is GCC 14. So you load this module, that puts the compiler in your user path, and then you compile the code. And what is highlighted here in red is basically the link to the CUDA BLAST library, which comes with the GSL. So that's very easy to do. And if you're interested to look into the full example, it is available at this link over here. I'm not going to have time actually to go over all these examples in details. Namely, I'm not going to compile and run them, but basically the idea is to provide you with the reference so that you can experiment in your leisure after the presentation. So the GPU version of the code is also available. In order to compile and then run the GPU version of this code, you will need to load also a CUDA module, which would put the CUDA BLAST library on your path so that you can link to that. So then the only thing which changes over here are these linking additions to the compile command. And once you execute that, you're going to have the executable score qblast.x in your environment, and then you can run it. Again, the example is available in this link over here. And also, because we don't have that many people, I just would like to remind you, if you have any questions, please feel free to interrupt me at any time and ask your question. We can make actually the presentation a little more interactive because we don't have that many people. Another approach for parallelizing your code is to use, like I mentioned previously, the OpenACC, and OpenACC here stands for Open Accelerator. And this is a programming standard for doing parallel computing on NVIDIA GPUs, basically. So the idea of this is really to simplify the GPU programming. You can think of the OpenACC really as a layer which stands between your application and the bare bone GPUs, because it allows you, with a very simple addition to your serial code, to parallelize it and take advantage of the GPU acceleration. So, like I'm saying here, in this line over here, the basic approach is really to insert special comments, which are directives. And for example, if some of you are familiar with OpenMP, which is the open multiprocessing, it provides a similar way to parallelize your program, but here on GPU level, not on CPU level. And like I said, it is very straightforward, and it is really possible for the software engineer or the programmer to create efficient application with only a few additions to a serial code to make use of the GPUs. OpenACC is specifically written to parallelize C or C++ and also Fortran code using GPUs. And here on this slide, I'm showing just two snippets of such code, which also parallelizes this single precision A multiplied by X plus Y operation. And over here we show parallel snippet of using C code, and this is again a parallel code which uses Fortran syntax for using OpenACC. So these examples have been taken actually from slides which were from a workshop on OpenACC, and the link is provided over here. You may take a look over there, and although they're from several years back, quite a lot already, this is a very good way to parallelize your C or Fortran applications if you have such. So how you compile with OpenACC? So on this slide we show how the compiling command would work. So I wrote a very quick example which uses a Fortran code and implements OpenACC to illustrate how this can be used on the cluster. And if you go to the link which is included here in this slide, you will see the example which includes details on how to compile and how to run it and eventually submit a job to the cluster using the compiled code. So here the important point is that in order to use Fortran with OpenACC, you need to load a module which provides access to the NVIDIA HPC toolkit. And this toolkit, in addition to some very good compilers, which also include the compilers from the Portland group or the PGI compiler, if you're familiar with that, it was absorbed by NVIDIA and now it is part from this NVIDIA HPC toolkit. Just the long story short, you need this module to be able to run Fortran applications with ACC, OpenACC. So to compile the code, you use the NV4 compiler, which comes with this module, and then to link to the OpenACC library and to instruct the compiler to make use of the OpenACC directives, which are included in the source code. Actually, you have to include this option over here, which is just -ACC. And once you do that, you will end up with executable, which is linked against OpenACC, and then you can run it on the GPUs. So that's actually the whole idea of this. On this slide, I'm going to talk about some examples, in particular using programming languages to make use of GPUs. And I just want to mention some of this which are included on the list. So all numeric frameworks, common frameworks like MATLAB, Mathematica, and I think even others like Maple and so on, it has been actually pretty popular in the past. I'm not sure that many people use it, but they have the ability to use GPUs. Languages like Fortran, C and C++ and Python actually can make use of GPUs using all these approaches, which included here. I'm not going to go through the complete list, but pretty much every single language that you're using for your computations nowadays has the ability to accelerate the applications using GPUs. So that's actually the major point here with this illustration. So now I'm going to focus a little bit talking more about how you in practice use programming languages to write a code which accelerates your applications. And again, NVIDIA wrote the CUDA, which is the Compute Unified Device actually CUDA, which is the Compute Unified Device Architecture. So basically, the CUDA platform is a software layer which gives direct access to the GPUs. And initially, it was designed to work with programming languages such as C, C++, and Fortran, but it can work also with Python. CUDA is an accessible platform and doesn't allow anything special besides installing the CUDA libraries, which come from NVIDIA. And again, the CUDA toolkit really includes GPU accelerated libraries, also compiler, and guides which come to instruct you how to parallelize your applications. And here we're including a link to the NVIDIA documentation. If you're interested in learning more details about this, there are a lot of material which includes tutorials and examples how to use CUDA to parallelize your applications. And in this slide here, I'm giving a very quick example how to parallelize, for example, C code. If here you have your serial application or serial code, this is just a snippet from a code which again performs that operation, which we're using as a basis of our examples here. This is the SAC pool, which is again the single precision, a constant a multiplied by x plus y, and x, y have vectors here operation. So in CUDA, in particular in C, this can be done just by adding these lines over here, which simply instruct the application how to handle that specific arrays over here and to transfer this memory to reserve specific memory on the GPUs and to offload the computation over there. So I have an example which shows how to compile this application. You have to load CUDA module. In particular, this module basically supplies the latest CUDA version that we have on the cluster currently, which is CUDA 12.4. I think we have to update our drivers to be able to run actually the latest CUDA, which is 12.6, which is going to happen maybe next year at our next cluster upgrade to Rocky 9. But just continuing with this example, once you load the module, then to compile it, you use the NVCC compiler and simply compile your code. Here, one thing to remember is that you have kind of a specific extension to your source C code, which is CU, which instructs the compiler that that would be a CUDA accelerated application. And again, the full example is available on this link if you go over there. But let me just show you, because there are also some other examples which are very interesting. So if not already, so this is a link to our GitHub repo. In particular, these are examples which are related to GPU computing. And the specific example that I've been talking about over here is this one, which illustrates how to use CUDA on the cluster. And this is the source code, the C code. This is the instruction how to compile it. And here we have job submission script, batch job submission script, which tells you how to submit the job to one of the available GPU queues that we have in the cluster. But I'm just going a little bit ahead of myself. But I just decided to pull this link over here because this GitHub repo in general includes many good examples for various things that we have in research computing. Okay, so let's just go back to the presentation. So we add another language to our arsenals of languages. So on this slide, I'm giving an example about using Python. So Python can also make use of GPUs, and one of the easiest way to do that is to use the Numba library, which provides many cool features. Actually, it provides the ability to compile, for instance, portions of your Python code. Let's say you have a specific function which you want to accelerate, and you just can tell the interpreter to vectorize your code with a command like this, and it will compile this function and can offload the function, for instance, to GPUs, and then you would be able to run it. So I have also a complete example for this, which includes the full code and also instructions on how to compile and run it. And Numba is really a great library. It allows you to run on CPUs and GPUs, but the important point is that it allows you to compile some parts of your Python code so that it can be executed much faster, because Python is just like kind of an interactive language which in some cases could be pretty slow for scientific computing. So now I'm going to focus on how specifically to execute your GPU workflows on the cluster. So we have compute nodes which have NVIDIA GPUs, and like I mentioned, we have A100 and H100 GPUs, which are one of the newest GPU cards which are available from NVIDIA. And the nodes on the cluster are organized in partitions, and the available GPU partitions that we have are the GPU partition, which has currently 36 nodes, which each node has 4 A100 GPUs. We also have the GPU underscore test partition, and this partition in general is intended to just test some of your applications or for developing purposes. I just like to make the distinction first between the different partitions. So the partition that we have available for general use is the GPU partition, which includes A100s. In other words, each node has 4 A100 GPUs, and it's available to all users that have access to the cluster. The problem with that would be, as such, it can be very busy, and sometimes if you want to request GPUs, it can take significant time to be pending. The GPU test partition, on the other hand, is not really intended for some kind of heavy-duty applications, GPU applications and computations, because the idea is simply to give the ability to more people to experiment with GPUs, and we partition every single GPU into 8 slices or 8 GPUs in a so-called multi-instance, so they are MIG partitioned. But the caveat here is that you can use only a single slice of a GPU, which may not be good for your computations. The GPU requeue, on the other hand, gives you the ability to the greatest pool of available GPUs, because this queue uses the spare cycles of PI-owned GPUs, which are not used by the PI labs. So on that queue, you have quite heterogeneous GPU environment we have, but this is the only queue which would allow you to use H100s, which are actually owned by various groups, like also the Kepler cluster has this, and if some of these are not used, if there are some idle nodes, they can be used. So in order to request a GPU with specific brand, let's say you need for your computation H100s, you have to put some, I think, some restriction on, or some additional flag when you submit your job, how to request specifically nodes which have H100s on them. So I think this link here, which is in the slide, provided in the slide, contains all this information in a lot more details, and also with some specific examples, for instance, how to request GPUs with specific GPU brand and things like that. So this can be very useful. So on this slide here, I'm going to focus on how to run GPU jobs. And the first mode, which is good for GPU computing, is the interactive mode, or submitting interactive jobs. And this can be done by using the salloc command, followed by the options which are given here in this example. So in this example here, -p would request the GPU underscore test partition, and then --grs GPU column 1 would instruct the schedule to reserve 1 GPU for your computation. And here with the mem option, we request 4 gigabytes of memory, the dash block capital N1, make sure that we are going to use 1 node, and the -t here followed by 60 tells the job schedule to request only 60 minutes. So that's that. And then once you submit that, then you're going to land on a GPU compute node, okay? And that GPU compute node is going to be part of the GPU underscore test partition. And now you can pick and see what happens on that node, and see, for instance, if somebody else is running GPU jobs, you can use the NVIDIA dash command to display the current snapshot of the jobs, the GPU jobs that run. Another command is nvtop, which is also useful. This is equivalent to the top command, which would give you in real time the GPU usage. You should already know this, but once you submit your job to the cluster, and once it starts, then from another terminal, you can SSH directly to the compute node where your job landed, and then you can observe in real time, for example, how your jobs are doing. Let's say you start one job, GPU job, and then when you see the name of the node where your job lands, you can do ssh.node and run nvtop or NVIDIA SMI or whatever, monitor your jobs in real time. Now we continue with running jobs again. To be able to compile your code and use GPU resources, most likely you have to load the CUDA module, and the CUDA software modules are, which modules are available, you can see through this command, module available CUDA /, and this will display the modules, the CUDA modules which are available in the cluster. The latest one is CUDA 12.4, which is the default one. And when you, for instance, load this module and type, let's say, you can check which, for example, compiler is used. It's gonna just show the path to the NVCC compiler, which is in the cluster. Also, some applications like CUDA DNN library, which is required for, in particular for artificial intelligence applications and deep learning libraries and so on. So basically, this is provided separately, but what I would like to mention is that this library is also matched with a specific version of the CUDA. So you can, if you need this library first, you need to load the specific CUDA module as well. So this is a very quick example on how to run GPU jobs on the cluster. In particular here, we show this in interactive mode. And for that specific example, we choose to run TensorFlow on GPUs using Singularity. So these are the steps. You jump on a login node when you log into the cluster. Then if you want to start interactive session, for example, you use this command over here. And what is highlighted in red here is relevant to GPU computing. So the first thing is to select a partition which is GPU capable. Here for this example, we choose GPU_test. Then you request the number of GPUs that you want for your application. Everything else we already talked about. So in order to run that specific application, you will use Singularity on the cluster. Singularity is a container framework which allows you to run containers, in particular Singularity containers, but you can pull also Docker containers. And this is what we do here in this example. We pull the, well, a specific version of TensorFlow from the Docker repository, from the Docker hub, and the command for this is this command over here. To do this, you do Singularity pull the name of the image that you built when you pull the image from the Docker hub, and then we, in that specific case, we use TensorFlow 2.13, which is GPU capable. To run some examples here, I clone some examples from the Keras repo, which includes some neural nets and other examples which can illustrate the usage of TensorFlow. So in order to do that, on the compute node, which is the GPU node, you do Singularity sec, and then to make sure that you're using the GPUs which are on the host, you do --nv, and then followed by the name of your Singularity image, and then the specific commands that you want to run, which in this case is Python, and then we run some example which do training of a neural net from the examples which are included in Keras. So I know that this may sound a little bit of a little bit complicated, but the complete example is available on GitHub. If you go to this link, you're going to find the example over there. So this is, on this slide here, I'm giving an example for running GPU jobs in a batch mode. Previously, we talked about running jobs in interactive mode, which is good for some very quick computations using GPUs, or for doing testing, so that you make sure that your code works well before you submit large-scale GPU computations to the cluster. So again, this example here highlights the relevant parts to the GPUs. So here you include the partition name, which is sbatch-p, the partition name. Here the usual stuff in terms of requesting CPUs. But what is relevant to GPUs is this: by sbatch:\grs equal to GPU column 1, you request one GPU. And then, because like I said, in this example, we are running through Singularity, to use the GPUs on an image, you need to add to your command the option --nv, and then whatever your command is. Again, I have to mention the use of NVIDIA-SMI or NVTop to monitor your jobs. So basically, once you submit your job, you're going to get a job ID, which would allow you to see where your job went, in other words, on which GPU node it landed to be executed. Once you see the name of the host, you, from another terminal, you can, like I said previously, ssh.host, and then on that host you can run the NVIDIA-SMI or NVTop commands, so that you can observe the execution of your workflow in real time and see and confirm if everything is executed correctly. So at the end, I just want to talk a little bit about multi-GPU jobs with MPI, or in general about doing multi-GPU jobs, where the GPUs can reside on the same node or can even reside on separate nodes, in other words, to enable multi-node, multi-GPU computing. So I know maybe this is a little more complicated, but I just want to mention this because the push is to do a large-scale GPU computing. Like I said, on a single compute node, you can have maybe 4, or in some cases, I know there are architectures which allow for 8 video cards, 8 GPUs to be, GPU processing units to be on the same node. But still, if, let's say, want to train, for instance, a very large language model, that would require scaling up to thousands of GPUs, so that you have to use multi-node computing and multi-GPU computing, where the GPUs reside on multiple nodes. So that's actually the basic idea here. In other words, you have interconnect, which is infinite band optical fiber, which connects the nodes. And you need some kind of protocol which allows you to do the communication between the GPUs. So if you're familiar with MPI, which stands for Message Passing Interface, basically MPI is kind of the de facto protocol for allowing multi-task computations. So in this scenario, basically, the idea here is to use all the GPUs on a single node, let's say, okay, and then for the communication between the nodes to use MPI. I know it sounds quite complicated, but if you get into this, it's going to make more sense. So here I'm just including a very quick example which illustrates how to do that. So let's say if you have application which can make use of multiple GPUs, which may or may not reside on the same node, the command to compile this is, for example, if this is a C application, in that case, you compile it with this command, which is mpi-cc, and your specific application. And then once you create the executable, you launch it through mpi run -np, the number of processors that you want to use. So basically what happens in that scenario over here, like illustrated here in this cartoon, you have four different nodes where, just for the sake of the argument, each node has a single GPU, and then you can use for your computation all the four GPUs which are connected through where they communicate through MPI. So this is example script, job submission script, which would illustrate how this scenario can be realized actually in practice. So that specific example uses two nodes with four MPI tasks and four GPUs per node. So basically, in order to run that, you need to tell the job schedule to reserve two nodes, and you're going to say that you want to have four tasks on each node. So overall, you're going to have 8 tasks, right? And then you request also 4 GPUs per node. You have to request also the memory per CPU, because the MPI is a distributed parallel programming model, which means that each of the tasks has its own map of the memory. In other words, if you want to communicate, let's say, a variable from one task to another, you have to explicitly pass it or communicate it. That's why we need the MPI for the message passing. And then let's say we run, for the sake of the argument, on GPU test. Okay? In order to make this happen, you need to load a compiler, a GCC module, and also on top of that, because we're using MPI, you will need to load also MPI library. In that particular case, this is OpenACC, and OpenACC is CUDA aware, which means that it is built so that the GPU computations are enabled. So you need to load also this module, the long story short, and then this is the actual command which runs your specific application. So we are done. Pretty much this is everything that I have, and these are some general resources that we have on this webpage over here, on this slide over here. This is our documentation, and you also have the ability to submit some tickets through this email address, and we also have office hours and also some upcoming trainings. So guys, thanks a lot for bearing with me in all these technical glitches that we had, and thank you very much for your attention.